Okay, let's talk about, let's talk about sensitivity and specificity. So you're going to read a lot about these concepts throughout your program in various papers. So in many clinical tests report how sensitive they are at detecting the disease and how specific they are to help confirm or refute presence or absence of a disease or a condition. So it's important to understand a few of the terms that go along with it. So a true positive is that the patient has the disease that they test positive. A false positive is that you falsely say they have it when they don't have it. And then as so on, you can see with true negatives and false negatives. So sensitivity of the test is it's the test's ability to correctly identify those patients who have the disease. And you can see how it's calculated. It's taking the true positives over the true positive plus the false negative. So for example, a test with 80% sensitivity detects 80% of the patients with the disease, but it's going to miss 20%. So that may be good in some circumstances. If you have a test that's very sensitive, and it may have a high sensitivity means it has a low false negative rate. Now, specificity refers to the ability of the test to correctly identify those patients without the disease. And you can see the calculation there. So if a test with 80% specificity correctly reports 80% of the patients without the disease test negative. So in terms of true negatives, but it's still going to detect 20% without the disease are correctly identified as testing positive. Now, the positive predictive value is how likely is it that the patient has the disease or outcome given the test result is positive. And you can see the formula there. And then you can see the negative predictive value is essentially just the opposite. It takes the true negatives plus the true negatives over the false negatives. And then you have a likelihood ratio, which is how much more likely is it that the patient who tests positive has the disease compared to those who test negative. So that's sensitivity over 1 minus the specificity. So let's look at an example here. This is a 2x2 table of results of different radiology exams in confirming or refuting the pulmonary embolism diagnosis. Okay, so what they have here is that you've got this 2x2 table. These are frequencies of findings. This would be an abnormal finding, a normal finding here, and then they have a true positive, true negative. And so here they have a test positive, and they have a true positive. You have the number there. And then you have test positive, but they have a true negative over here. Okay. So what they found here was that 87 of the studies were non-interpretable by the radiologist. So that's this number right here. There was 90% sensitivity with this particular test for confirming the diagnosis of pulmonary embolism. So what that means is they took this 164 here and over 183, which was the true positives, the 164, plus the false negatives. Right here. Okay, so that gets you that number. And the specificity was 95%, which is taking the true negatives, which is this 524, divided by the true negatives, plus the false positives. So it's that 524 plus that 30. I'm sorry, it's the 524 plus the 19 there. It's calculating that number for you. Okay, and then and then you can see that they've also calculated the positive predictive value, which is slightly different than sensitivity, and then you have the specificity, which is slightly different than the negative predictive value. And if we calculated the likelihood ratio, it was equal to 18. All right, what are receiver operator characteristics? So this is a term that dates back actually to after Pearl Harbor, and it was devised by the radio receiver operators after the attack to determine how U.S. radar had failed to detect the Japanese airplanes. And it's a very widely accepted method for selecting optimal cut points for diagnostic tests and comparing the accuracy of diagnostic tests. And so it's calculated by taking the sensitivity and specificity of a test at every possible cut point and then plotting the sensitivity against the 1 minus the specificity over here, okay? And then you can use this curve to select an optimal cut point values for a test result and to evaluate the diagnostic accuracy of the test and to compare the usefulness of different tests. So you'll see this later in the lecture when we talk about the APFL's PONV criteria. Also, it's been used with development of the stop bang questionnaire in terms of identifying an optimal cut point for the score and different scoring strategies for that. So an ROC with 100% perfect discrimination would be this line C. Line B would be a typical clinical test. It's probably a ranging of 0.5 to 1. And then a line of zero discrimination is at 50% right here. So this particular one shows a ROC curve of 0.7295, so about 72% right there, that would make that probably a decent test.